Sketching out this analogy, you're picturing a fundamental particle, maybe like an electron, as a kind of ball rolling through space.
Mm-hmm.
And in this picture, this rolling, it's not just movement. You suggest it somehow generates a rotating magnetic field.
Right. That's the intuitive idea.
Which then, in turn, produces these oscillations we associate with its quantum frequency. So our mission in this deep dive, using the sources you shared, is to really dissect this.
Let's take it apart.
See where it lines up or maybe where it breaks down compared to the established physics concepts in your material and, pull out the key insights.
That's right. And it's always tricky, isn't it? Trying to map quantum weirdness onto these, classical mechanical pictures we can actually visualize.
Definitely.
But exploring these analogies, even flawed ones, is often how we start to get a handle on things. Your sources give us a great framework for examining this specific one.
Absolutely. So let's start by breaking down the analogy itself piece by piece as you laid it out. We've got three main components. The particle as a rolling ball, its spin causing a rotating magnetic field, and then that field generating oscillations of frequency.
Okay, yeah. Let's look at what your source material says about each of those. The rolling ball idea. Well, that immediately suggests something physical, right? An object with actual size, located somewhere specific, and it's classically rotating and moving.
Yeah, like a tiny billiard ball spinning as it moves. It would have kinetic energy from moving and also from spinning.
Exactly. A very tangible image.
But now, how does the source describe actual particle spin in quantum mechanics? Because that feels like the first place the classical picture might wobble a bit.
It absolutely is. The source is very clear. Quantum spin is intrinsic angular momentum. It's fundamental, but it is not classical rotation.
Not like a top spinning.
No. Think about electrons. In the standard model, they're point particles. No physical size to literally spin around an axis.
Okay, so no radius.
Right, but they do have spin, and it's quantized. It comes in fixed amounts, like spin 12 for an electron, spin 1 for a photon, discrete values.
Got it. So the rolling isn't literal spinning. What about the rotating magnetic field part? Does that hold up better?
That part connects more closely. The source material confirms that charged particles with spin, like our electron example, do inherently possess a magnetic dipole moment.
So they act like tiny magnets.
They absolutely do. And your analogy's idea that a classically rotating charged object would generate a rotating magnetic field, that's correct in classical physics.
Okay.
And the source also notes, interestingly, that even neutral particles, like neutrons, have a magnetic moment.
Which is strange if they have no charge.
Right, but it comes from their internal structure, the charged quarks moving around inside.
Oh, okay. That makes sense. And the third piece, the oscillations of frequency. How does the source connect frequency to particles in the quantum realm?
This ties straight into wave-particle duality. The bedrock here is the Planck-Einstein relation, E equals hf.
Energy equals Planck's constant times frequency.
Exactly. So the frequency f is directly linked to the particle's total energy. It's a core aspect of its wave nature, leading to things like the de Broglie wavelength.
Okay, so we've got the analogy laid out and the corresponding quant concepts from your source material. Now, this is where it gets really interesting, I think. Does your source material point to anything in actual physics that kind of echoes this intuitive idea of internal rolling or some inherent motion inside the particle?
It does. And this is where the source introduces a really fascinating, though quite subtle concept. Zitterbewegung.
Zitterbewegung.
German.
Yes, it means trembling motion. According to your sources, Zitterbewegung is probably the closest thing we have in relativistic quantum mechanics, though still theoretical and, analogical in its own way, to your idea of an internal rolling or jitter.
Trembling motion. Sounds intense. What exactly is it supposed to be? It's described as a theoretical, incredibly rapid oscillation, a sort of trembling. Your sources specify it's predicted for elementary particles, particularly fermions.
Spin 12 particles, like electrons.
Right. The ones described by the Dirac equation, that's the key. The Dirac equation, which is the relativistic quantum equation for these spin 12 particles.
So it comes right out of the math that describes how these spinning particles behave when moving very fast near light speed.
Exactly right. And this Zitterbewegung isn't just random jiggling. It has a very specific, very high frequency.
Yeah.
The formula given in the source, let's see, it's ASIA equals 2 MEC goes, or if you use SAZ for frequency, it's SCA equals 2 MCAH.
Oh, wait, MCAA, that's rest energy, EMCS.
Precisely. The frequency of the Zitterbewegung is directly proportional to the particle's rest mass energy. It's basically twice of the rest energy divided by Planck's constant.
Wow, so a particle just sitting there fundamentally trembles at a frequency
Yeah.
set by its own mass. That's
Right.
wild. What kind of motion is it? Is the particle physically shaking?
Well, the source clarifies it's not a classical trajectory like vibrating back and forth. It actually arises from the mathematics of the Dirac equation itself.
How so?
It comes from interference between different parts of the solution specifically, components linked to positive and negative energy states, which are a feature of relativistic quantum theory.
Mhm.
So it's often thought of less as literal movement in space and more like an internal clock ticking extremely fast, or maybe an inherent jitter in the particle's properties, like its position measurement.
Okay, so if we sort of tentatively map the analogies rolling onto the Zitterbewegung, the source suggests the particle does have this intrinsic superfast oscillation linked to its mass. But the analogy had the magnetic field producing the frequency. How does Zitterbewegung connect the magnetic field and the frequency?
Okay, let's trace that connection in your source material. We already established that an electron has spin and therefore a magnetic dipole moment.
Right, the tiny magnet.
So if the electron is undergoing Zitterbewegung, this intrinsic magnetic moment would essentially tremble or oscillate right along with it.
Ah, okay.
The source suggests one way to, again, visualize this analogously is like an internal circulation of charge or energy, kind of like a tiny internal current loop.
A conceptual current loop, not a real wire.
Exactly, a conceptual current. And that effective internal current associated with the Zitterbewegung would generate a local magnetic field. As the Zitterbewegung happens, the direction or strength of this field would oscillate.
At the Zitterbewegung frequency.
Precisely. At that very high frequency, 2 Begums for each.
Okay, so the insight here from the source is crucial. The oscillating magnetic field isn't necessarily the cause producing the Zitterbewegung frequency.
That's a key distinction the source makes, yes. It's less cause and effect and more like they're both symptoms of the same underlying thing.
Co-manifestations.
Yeah, that's a good way to put it. The oscillating magnetic field and the Zitterbewegung frequency are both consequences or co-manifestations of the fundamental relativistic quantum dynamics described by the Dirac equation for that spinning particle.
This brings up a really important question then. Is this Zitterbewegung frequency, the 2-meter-ADO one, the same as the overall quantum frequency we usually talk about? The E total from Ebrad.
No.
Right.
And the source is careful to make that distinction. It's crucial. Remember, the de Broglie frequency is F equal H. That E total includes all the energy, rest energy, plus kinetic energy if the particle's moving.
Right.
But the Zitterbewegung frequency, Fz equals 2 metal C cut C forge, is tied only to the rest mass energy, MCFBO.
So for a moving particle, these two frequencies would generally be different.
Yes, definitely different for a moving particle.
So maybe a particle has like two fundamental frequencies at play, one internal, one external.
That's an intriguing possibility the source touches upon. It speculates that Zitterbewegung could be seen as a kind of internal carrier wave, if you like, a fundamental oscillation intrinsic to the particle just sitting there.
And the de Broglie wave.
The de Broglie wave, which governs how it moves and interferes through space, might be like a modulation on top of that internal jitter. The source mentions this idea isn't entirely out of the blue. De Broglie himself explored ideas about internal periodic motion being the basis for quantum waves in his theory of the double solution.
Fascinating. Now, let's circle back to spin. You said Zitterbewegung comes from the Dirac equation, which is for spin 12 particles. How deep does that connection go? The analogy links spin directly to the rotating magnetic field.
The source material really emphasizes that spin is absolutely central here. It's not just incidental. The Dirac equation, the very mathematical framework that predicts Zitterbewegung, is specifically the relativistic theory for spin 12 particles.
What about spin 0 particles?
According to the source, scalar particles, spin 0, which are described by different equations like the Klein-Gordon equation, don't show Zitterbewegung in the same way. It's the multi-component nature of the Dirac wave function, the mathematical structure needed to describe spin-up and spin-down states that allows for the kind of interference between positive and negative energy solutions that leads to Zitterbewegung.
So the analogy's intuition, linking spin to some kind of fundamental oscillation or internal dynamic, that actually taps into something real in the physics.
It seems so. It correctly senses a deep, almost foundational link between a particle having spin and it exhibiting this kind of intrinsic oscillatory behavior predicted by the relativistic theory.
Okay, so the analogy, while intuitive, clearly isn't a perfect fit. It captures some essence, but misses details. What are the main limitations your source material points out when comparing the simple rolling ball to the actual physics?
Yeah, the source is pretty clear on the caveats if you take the analogy too literally. First, like we said, it's definitely not classical rolling or spinning.
Right, quantum spin isn't mechanical rotation.
And Zitterbewegung isn't a classical path. It's more like an oscillation of the particle's position operator in the quantum math, or a feature of how its wave packet behaves, not a tiny ball literally tracing a path.
So the ball is just a stand-in for internal dynamics, not a physical sphere.
Exactly. Second, related to that, particles like electrons are point-like in our best current theory, the standard model. They don't have a physical radius or volume like a macroscopic ball. The analogy hints at internal structure or dynamics, but not literal size.
Okay, point particle. What else?
Third, the source notes that the analogy maybe muddies the water on where the main quantum frequency comes from. That overall de Broglie frequency, its total, is usually taken as a fundamental postulate of wave-particle duality itself.
It's just part of the basic rules of quantum mechanics.
Right. It's not typically seen as being produced by something like radiation from a classically rotating magnet, which the analogy might sort of imply.
The origin is different in the formal physics.
And finally, as we discussed, in the Zitterbewegung picture derived from the source, the oscillating magnetic field is more like a correlated effect, a symptom of the Zitterbewegung, rather than the sole producer of the frequency characteristics.
Both arise together from the deeper physics.
Exactly, from the relativistic quantum mechanics of that spinning particle.
Okay, so quite a few significant differences. But despite all that, the source suggests the rolling ball analogy still has real value. What makes it useful then?
Well, according to the source, its strength is that it correctly intuits some important connections. It senses that spin is tied to magnetism. It suggests particles have some kind of built-in, intrinsic oscillatory behavior, and it tries to find a physical mechanism behind their frequencies.
And it points us towards concepts like Zitterbewegung, even if indirectly.
Precisely. As we mapped it out, Zitterbewegung seems to be the closest parallel concept described in the source material. The rolling part captures the oscillation idea of Zitterbewegung. The rotating magnetic field mirrors the magnetic moment participating in that oscillation. And the frequency produced, well, that finds its closest match in the Zitterbewegung frequency, 2 million C20, which is determined by an internal characteristic, the particle's rest mass.
Just like the analogy links internal motion to frequency.
Right. But, and the source hammers this home, it is just an analogy, quantum stuff is fundamentally non-classical. It doesn't capture the full mathematical picture, the subtlety. And crucially, the de Broglie frequency, E total, is still there. Distinct, fundamental, alongside the Zitterbewegung frequency, 2 million C20.
So the bottom line from your source material seems to be that this simple picture touches on a really profound idea. That fundamental particles aren't just static points. They have intrinsic dynamics, internal frequencies, deeply connected to their most basic properties like mass and spin.
Exactly. And spin isn't just some extra quantum number tacked on. It's woven right into the relativistic theories, like the Dirac equation, that predict these incredibly rapid internal oscillations.
So we started with this wonderfully simple image from your notes, a rolling ball generating waves, and this deep dive, guided by your sources, took us all the way to the theoretical concept of Zitterbewegung, this trembling motion predicted by the Dirac equation, intrinsically linked to a particle's spin and its very mass.
Yeah, the source material really underscores that spin is fundamental to how particles behave relativistically, how they vibrate effectively at their very core. It's not just an add-on property.
It leaves you with a really interesting thought, doesn't it? Consider this as you go about your day. If you have this Zitterbewegung, this internal oscillation tied purely to a particle's rest mass,
The 2 million series frequency.
and then you have the de Broglie wave governing how it propagates through space based on its total energy.
Just total frequency.
How might these two fundamental frequencies, one seemingly internal and the other governing external behavior, interact or combine? How do they work together to create the single reality of the particle that we actually observe and measure?
That interplay.
Yeah.
Yeah, that's definitely something to ponder.